Okay, so in the last lecture we have discussed about the uh, deflection, right? In the case of force vibration, and we also talked how this ratio of deflection with respect to which is called magnification factor, essentially how it varies with the frequency ratio, right? And we plotted a curve for that and studied that how this ratio is going to change with respect to the another parameter which is called damping ratio. So this curve that I drawn in the last lecture will help that how this resonance condition can be avoided, what is the value of amplitude considering the fact of having that frequency ratio in mind. Now we will talk a practical case in which we analyze again. Our interest is just to calculate the magnitude of the vibration under the operating condition and how we can resolve it and brought down the vibration level to a normal operating condition in which failure we can avoid failure, right? So now we will talk about rotating and reciprocating unbalance in case of force vibration, as we were discussing, right? Now where these kind of case are essential, if we talk about an electrical motor, a turbine, and in fact all other machinery which has rotating part, have some amount of unbalance left in them because of manufacturing inaccuracy. Deposition of material at a certain place gives higher density, and this ultimately causes a shifting in the center of gravity. So we cannot say that it is a perfectly balanced system. So some an unbalance would remain in such kind of system. So the final unbalance is measured in terms of equivalent mass rotating with its center of gravity at a distance, at some distance, and the centrifugal force generated because of this rotation of body is proportional to the square of frequency of rotation. The centrifugal force is maximum value which causes vibration, and in the last case which we said, which is f naught sine omega t, has taken place this sinusoidal excitation in any direction. Now if we try to plot a diagram in this respect for the discussion, we can say that this is the our rotatory element, right? And this is the reference axis, let us say, right? And there is that rotating unbalance which I said earlier is considerably, let's say, m naught, and at a distance e. Now what centrifugal force does it impose on the system? This is m naught omega square e from the conventional mechanics equation. Now so being set into the rotational motion of omega radian per second, we can say getting at different points. If this mass goes to different point moving around the circle, it shows various component of this centrifugal force and to create disturbance in upward and downward direction, right? Now so we could try to damp out the situation. Let us say that machine is been placed over a damper and a spring to control this force vibration motion, right? And now with this respect, how much vibration, if the stiffness of spring is k and this is c, so we need to relate this formula with the previous one as we have studied earlier about the this ratio of zero frequency deflection with the this operational deflection which we'll achieve here. Now so that force which is, I mean, in the zero frequency deflection case, last time I defined it by f naught by k. Now this f naught has been replaced in this case of rotation by m naught omega square e, which is a centrifugal force and which is responsible for the deflection in the system. So now we can see here this x is equal to, now the F naught has become m naught omega square E divided by k, and you can notice in all those formulas the basic part which is remain in the denominator of the section, which is omega by omega n square plus 2j omega by omega n square, right? Now one more thing, that transient part of the solution is same. If we talk about the transient state of vibration, so this system will remain in underdamped situation, right? All the case we have been discussed and we will discuss will remain in the uh, underdamped state, and this is how we can calculate our diffraction part. Now we can modify this formula further in terms of getting the amplitude right. So we can say it in that way. Suppose the actual mass of this wheel is m. So here one more formula to calculate this unbalance and create a proper equation in terms of the frequency ratio to analyze this reciprocation and generate the resonance condition to avoid failure of the system. We can derive this equation all in terms of the frequency ratio and this omega by omega n ratio and damping ratio, right? Now we can also see that as the omega by omega n, now we have to relate each and every situation where x is the deflection, how it depends upon the frequency ratio, and at the same time how it depend upon the damping ratio. Now if I calculate this here, we move it first. Okay, so now our equation is x is equal to m naught e by m, right, equal to omega by omega n square root times 1 minus omega by omega n square whole square plus 2 xi omega by omega n square. Okay, now let us get the sense that how we can evaluate. It will reflect the same curve as we have seen there. Now as I repeat every time that our endeavor is to remove the resonance condition, and this horizontal axis will always represent this omega by omega n, and this side this ratio x upon m naught e by m will go ahead. Now suppose the if omega by omega n holds a value of 1, we can have here the resonance situation. Now the difference from the previous case is that here we cannot have a zero diffraction situation, but in this case of reciprocating or rotary part we have a neutral situation, which signifies that this ratio can start from very from 0, right? Now for lower value of damping, right, we have this case of resonance. As we are going to provide the damping within the system for different values, this curve is going to get narrowed down. Now that means we are coming to a neutral situation as we are increasing the value of damping, but certainly we have to keep our discussion for the underdamped system, for the forced vibration case, right? Okay. Now similar thing we can talk of a reciprocating part, right? So the equivalence mass will remain the same situation. Consider IC engine in which piston through connecting rod connects piston with the crankshaft and it starts rotate. So that unbalance which you're supposed to have is in the piston part, right? So this omega square, now the centrifugal force, which is m naught omega square E, causes unbalance in the motion of crank. Now, it could be m naught omega square is sine omega t, which disturbs a lot, and so on. The discussion goes ahead with this centrifugal force. But the point is that whenever we are having this situation in engine which contains both rotary and reciprocating part, this unbalance causes undesirable vibration, which ultimately causes loss in energy. And so we need to keep this mind during the design stage, that this unbalance should be matched with the balanced part, and we don't have that much unbalanced force which causes unnecessary losses of energy. Now, uh, one more um, example of relative amplitude, if we can have here, is this is now we'll move to the concept of the basic concept of measuring instrument, and we will discuss at the end of this series how the vibration measuring instrument functions. Now, let us say again we will go this with this basic definition, right? Now, this part has come here. It is damping, and same the mass has been put in. Okay. Now, suppose this supports also goes down in this way. To find these values, we have to see this, that this relative amplitude is of our interest, that how much support goes down with respect to this mass, or this mass goes down with respect to this support. Now when this situation arises, suppose a measuring instrument has been put over a system which is in vibration motion already, and by putting this particular instrument to gauge the vibration within the system, you will see that with the system vibration translates into this instrument, and this instrument also has moved entirely. So when the system moves, we need to find the relative motion of this mass and this support as well, to ascertain the actual value of the vibration amplitude, right? So next formula is related to this part only, which says x by y is equal to under root 1 plus 2 xi omega by omega n square divided by root 1 minus omega by omega n whole square and 2 xi omega by omega n square, in that way. This is x by y case. Now if we talk of relative amplitude, as we all know that this is going to be x minus y, right? Now let us say this parameter be as let's say z. So we can get into the zone of formula, that how we can calculate it. Now the final result is, which is clearly dependent upon omega by omega n, and the base part remains same in each and every question, so we all know it. Now let us take a example of an automobile in that case. Now consider it, uh, uh, let's say an automobile has its own weight, right? And the shocker part, which is essentially the springs, goes around let's say zero point 0.1 meter, experience 0.1 meter compression under the influence of automobile's own weight. Now if we have to find the critical speed and amplitude of vibration at 60 km per hour, if the which is the general case in the practical situation, suppose the automobile's speed is 60 km per hour, right? And we need to gauge the vibration that system will have because of automobile's own weight. So one more thing we can have it here is, suppose the road profile is kind of the sinusoidal way, in this way, right? In this way, and the wavelength, that wavelength means distance between two peaks, right, which is essentially the part to design the road system, which is 14 meter, and amplitude of wave is 0.08. Now we need to find the amplitude of vibration. This is all we need to find out here. Now we can see here clearly that first part is to get the natural frequency. If we have a spring mass system here, so we can say this, that this is the automobile placed over a spring and it keeps moving in the forward direction in this sinusoidal kind of route, right, just for the sake of analysis. Now if it travels with 60 km per hour ahead, calculate the natural frequency of this part. As I said, since we have compression of a spring, so the natural frequency will be G by delta. So we can have here is 9.81 by zero point 0.1. So whatever be the result, this shows our natural frequency. Now we can see clearly that I hope you are aware of this formula of mechanics. V by 14. This represents the frequency of the system, not natural this radial frequency, but general frequency, which has the unit of hertz, and by this omega n divided by 2 pi. Now we can see that this V under this compression of spring, this is let's calculate the value. Suppose it is 10, so this will come out as 10 kilometers or something, right? So we have 10 by 2 pi into 140. So this is V is 70 by how much it is? It would be 70 by pi meter per second. Now we are talking about kilometer per hour, so multiplying by 18 by 5. So 14 into 18, it will come around something 80 kilometers per hour. Now the value of this excited frequency omega corresponding to a speed of 60 kilometer per hour, if we talk about, we will have the ratio of omega by omega n, right? So for this 60 kilometer per hour, so this is what came here is the natural frequency. Now we need to deal with the actual frequency in case of 60 kilometer per hour, and this you can quote as your resonance speed, to keep that in mind. So this you can note as your natural frequency. Now we are calculating the frequency corresponding to the 60 kilometer per hour in which our vehicle is actually moving ahead. So the formula which we can follow here is 60 into 5 by 18 to convert it into the meter per second range, and then again 2 pi by this wavelength 14, right? So we can have here 7.47. This is just a part of calculation. Now for the omega by omega n, what we can have here is 7.47 divided by 10. So 0.747 is what we are having here. Now with the help of this, as I said, that amplitude of this sinusoidal wave part is 0.08. But the ultimate fluctuation result within the system is as 0.1 meter. Now to get the actual deflection of the system having these things, this is 0.08, and we don't have any damping in this part. So the formula what we have been using here is the 1 plus 2 xi something, and xi is 0, so this part means nothing for this formula right now, right? And the denominators root will be gone out, and we don't have this under root also. Now this is 1 minus omega by omega n square. We generally take mod because we don't want to deal with the this what we can say this negative amplitude, so we place modulus right here. Okay, so we can have x is equal to 0.186. Now I would like to give a clear information regarding, we have three different amplitude here. Now this is the amplitude of this sine wave. Suppose this distance 0.1 meter is the compression of spring, and this result reflect on the automobile mass by 0.186 meter, right? So this we have to keep in our mind here. Okay, now one more thing in this part is that we can say this frequency that we calculated here, is the natural frequency of the system, which gives us a speed of 80 km per hour. Now, if we see the lighter bikes or car, which has been designed to run at a speed of 100 km per hour, it is the maximum speed of a particular vehicle, let us say, but we cannot drive it at this speed. It will start vibrating abruptly and ultimately result to any kind of failure. It could be engine failure, it could be meeting with the accident, uncontrolled motion. So we need to keep our limit in the safe side, as is been appeared in the question, that this is the 60 km per hour, which is the recognized speed. Now we can go with the resonance speed, which is 80 km per hour, and it gives very higher amount of vibration, right? So this is in this lecture we will stop discussion right here, and further we will take few examples of vibration measuring instrument, which is based on this relative amplitude part.